All right, folks, let's get started. So this week we're going to do the energy conservation lab. And what I'm going to have you do is twofold. You have two objectives this week. For both of them, you're going to be using a simulation on PhET that involves a skateboarder and a track. So what you'll do is you'll go to the appropriate module. And here's the pre-lab with some questions you should definitely answer. Here's the energy conservation portion. And again, to remind you, what you're dealing with is the idea of energy conservation, which is that the total mechanical energy before and after any action should be the same. So in the equation, K plus U is your mechanical energy. And if there are no non-conservative forces implying that, oops, well, that's annoying. It's implying that the work done by the non-conservative forces is zero. So that term goes away. Then you have the energy before equals the energy after. However, if you have non-conservative forces, things like friction or air resistance, you have to add this WNC term, which could cause your mechanical energy to be slightly different before or after, to the extent that the non-conservative force did work. And so knowing that going in, what we're going to do is two things. You're going to go to the skate park simulation. And the first thing you're going to do is you're going to figure out the coefficient of friction between the skater and the track. So you can go over here. There's an intro and all kinds of groovy things, but we're going to go here to this playground. That's going to give us the most ability to manipulate the skater and their environment. And you can see that what you can do is you can pull out pieces of track and move them around. You can even add additional bits and do all kinds of crazy, wacky tracks. And you can pick up the skater and you can drop her on there and she'll skate around back and forth. And eventually come to rest. That was my phone. Now, you have a lot of things you can adjust, right? You can adjust the shape of the track, and that will cause her to move around differently. You can also do things like turn friction. Like if I turn this thing completely frictionless, well, what's going to happen is my skater, if I put her at some location and let her go, she'll just rock back and forth, and she'll basically do it forever. You know, why will she do it forever? Because there's no non-conservative forces taking energy away from her. And so when she gets up to this highest point on the track, that's where she has all potential energy. When she gets down to the bottom of the track, that's where she's got no potential energy, but all kinetic energy. And along the way, the energy she has is sloshing back and forth between the two forms. You can see here in this little graph that as her potential energy goes up, her kinetic energy goes down, and vice versa. But that's because there are no non-conservative forces. If I turn this friction slider back up, what you will see is that as she slides, so the friction is slowly converting some of her energy into thermal energy. It's causing like the wheels of the skateboard to heat up, or the track to heat up slightly. And over time, what's going to end up happening is all the energy that she started with gets converted into thermal energy, leaving no mechanical energy left, and that's when she comes to rest. So you can adjust the amount of friction that she has available to her. Now, there's another button you can push. That's the stick to track button. And that's useful because sometimes if I do something like this, and I drop my skater, and she picks up enough speed, when she gets to the other side, she's going to slide off the track entirely. She'll lose contact with that track. And that might be of importance to us. So that stick to track option, depending on what we're doing, may or may not be useful to us. So how are we going to do the objectives that we're required to do? The first of which is to measure the coefficient of friction. Well, one thing to do would be to set up a track in some design that you are easily able to calculate the work being done by the friction, or to figure out the non-conservative work being done. So that the idea is, if I know how fast she would go at the bottom of my hill without friction, I can figure out how much energy goes missing when I turn on the friction, and then use that to calculate the non-conservative work. So that's one option you have available to you. However, I will point out something, and that's that if I were to do an experiment much like I had set up a minute ago, and let's say drop her from here to here, well, what's going to happen is I could do things like use the timer to measure the time, or the meter stick to measure the distance. But one of the things that I'll run into is that along this curved track, friction is doing work. But in order for me to find the work, I'd have to use F dot D, and the force and the distance are not always going to be in the same direction. And what's more, the length of the path, the distance traveled, will be difficult to calculate. So it may be in your best interest when you do this to maybe pick a track that is easily identifiable. In other words, maybe I would like to, if I try this again, if I let her go, I can figure out at the bottom like what her speed is, but that's her speed with friction. If I turn the friction off and try it again from the same height, you'll notice she's going slightly faster at the bottom. And the difference I can attribute to the amount of work being done. But in order to do the work, I'd have to be able to figure out this curvy distance, which is going to be hard. So maybe you want to make sure that you design your track with a shape where calculating the distance is a little bit easier. Just a thought. So that's one of your objectives, is to do that. Figure out, based on some experiment that you've designed, how much work got done. The second thing that you're going to do is you're going to build a track with a loop in it. So maybe if I do this, so I want a circular loop. Or at least as near to circular as I can make it. And so you can see that I'm having it loop all the way around in a fairly circular loop. And of course, if I pick her up at the very, very top and I let her go, she can zip all the way through that loop. Now, I had the stick to track option on. If I turn that off, if I start her from high enough, she'll make it through the loop anyway without falling off the track. But if I start her at too small of a height, she may fall off the track before she gets up to the top. And we learned how to solve that problem of how fast you have to be going in order to do that, right? We learned in chapter 6 that if you're at the top of the track, there are two forces acting on you. There's a normal force and gravity. And that means that F equals ma suggests that if you're in circular motion at the top, we could write that expression. However, if we slow it down to the minimum possible speed, that means that the normal force would have to lower itself to the minimum possible normal force, which would be 0. And so if we solve that for v, we find that the minimum velocity required is the square root of rg. And so what you would like to do is derive an expression for how high up the track I have to have her when I release her so that she doesn't barely manages to stay on the track without falling off the top. And that means she's going to have this speed at the top. One of your homework problems, I believe, was quite similar to this. So you might want to consult that homework problem. But your goal is to determine the relationship for the minimum height. Try doing that with the friction off. And verify that relationship. So first, derive the relationship. Second, set up the experiment to demonstrate that that's going to be borne out in this procedure. So hopefully, what I've asked you to do is clear. If it's not, you know where to find me. My emails are open. Please note that in objective 1, I want you to do the experiment twice. Since the friction is selectable, try doing it once with the friction set at the midpoint of the slider, and the second time, crank it up to its maximum. Let's see what range of frictional coefficients this simulation utilizes. All right. Well, I guess if there are no other questions, I'm going to leave you guys to it. But hopefully this is fairly straightforward.